Section 5.2, Quantum Theory and the Atom. The objectives are to compare the Bohr and quantum mechanical models of the atom, explain the impact of de Broglie's wave-particle duality and the Heisenberg uncertainty principle on the current view of electrons in atoms, identify the relationships among a hydrogen atom's energy levels, sublevels, and atomic orbitals. Some vocabulary to review will be atom, and some new vocabulary will be ground state, quantum number, de Broglie equation, Heisenberg uncertainty principle, quantum mechanical model of the atom, atomic orbital, principal quantum number, principal energy level, energy sublevel. The dual wave particle model of light accounted for several previously unexplainable phenomena, but scientists still didn't understand the relationship among the atomic structure, electrons, and atomic emission spectra. And recall that hydrogen's atomic emission spectrum is discontinuous. That is, it is made up of only certain frequencies of light. Why are the atomic emission spectra of elements discontinuous rather than continuous? Niels Bohr, a Danish physicist working in Rutherford's laboratory in 1913, proposed a quantum model for the hydrogen atom that seemed to answer this question. Bohr's model also correctly predicted the frequencies of the lines of the hydrogen's atomic emission spectrum. Building on Planck's and Einstein's concepts of quantized energy, Bohr proposed that the hydrogen atom has only certain allowable energy states. The lowest allowable energy state of an atom is called ground state. When an atom gains energy, it is said to be in an excited state. Bohr also related the hydrogen's atom energy states to the electron within the atom. He suggests that the electron in a hydrogen atom moves around the nucleus in only certain allowed circular orbits. The smaller the electron's orbit, the lower the atom's energy level, or energy state. Conversely, the larger the electron's orbit, the higher the atom's energy state, or energy level. Thus, a hydrogen atom can have many different excited states, although it contains only one electron. If we kind of look at Bohr's idea in figure 5.10, the figure shows an atom that has one electron. Note that the illustration is not to scale. In the ground state, right, here's the ground state, the electron is associated with the lowest energy level. When the atom is in the excited state, it is associated with a higher energy level. And notice kind of how we have these concentric bands around the nucleus, and how that in the ground state it's closest to the nucleus, or at some energy level closer to the nucleus, but in its excited state it jumps up an energy level. And again, the only way that we can go ahead and make an electron jump is with energy. We'll talk about that in a little bit. So in order to complete his calculations, Bohr assigned a number in which we call n, and we call that a quantum number, to each of its orbits. He also calculated the radius of each orbit. For the first orbit, the one closest to the nucleus, we call n equals 1, and that has a radius of 0.0529 nanometers. For the second orbit, he calls it n equals 2, and we can see that there's an increase in the radius there, so on and so forth. We can go ahead and also look at this table to kind of go ahead and break that down. So as we get into those little concentric bands, right, whether it be first, second, third, so on and so forth, right, we call those bands either N1, N2, N3, N4. So Bohr suggests that the hydrogen atom in the ground state, also called the first energy level, when its first electron is in the n equals 1 orbit. In the ground state, the atom does not radiate energy. When energy is added from an outside source, the electron moves to a higher energy orbit, such as the n equals 2 orbit, as shown below. We can take that n equals 1, and again, we could always just go ahead and jump that to n equals 2, n equals 3, n equals 4, 5, 6, and to n equals 7. All right, just by adding some sort of energy to it. Such an electron transition raises the atom to an excited state. When the atom is in an excited state, the electron can drop from a higher energy orbit to a lower energy orbit. As a result of the transition, the atoms emit a photon corresponding to the energy difference between the two levels. Again, if we wanted to go ahead and find out, right, we can go ahead and say that the change in energy is equal to the higher energy minus the lower energy, which is equal to the energy of that photon that was emitted. And we could also go ahead and find out what that frequency is. Now, if you remember back from 5.1, if we know the frequency, we could also go ahead and find the wavelength of that light. Because only certain atomic energies are possible, only certain frequencies of electromagnetic radiation can be emitted. You might compare hydrogen's atomic energy states to rungs of a ladder. A person can climb up or down the ladder only from rung to rung. Similarly, the hydrogen atom's electron can move only from one allowable orbit to another, and therefore can emit or absorb only certain amounts of energy corresponding to the energy difference between the two orbits. Figure 512 shows that, unlike rungs of a ladder, however, the hydrogen energy levels are not evenly spaced. Right? To kind of give you an idea, right? Rungs of a ladder kind of look like this, right? You step up, and they're all spaced equally. However, when we're talking about that of an atom, those energy steps are not evenly spaced. As we can see, that big gap from 1 to 2, and that gap gets smaller from 2 to 3, and smaller 3 to 4, and smaller 4 to 5, etc., etc., etc. Electron transitions from higher energy orbits to the second orbit account for all the hydrogen's visible lines, which form what we call the Balmer series. Other electron transitions have been measured that are not visible, such as the Lyman series, which fall in the ultraviolet range, in which the electrons drop into the n equals 1 orbit, and the Paitian series, which fall in the infrared spectrum, in which the electrons drop into the n equals 3 orbit. Bohr's model explained hydrogen's observed spectral lines. However, the model failed to explain the spectrum of any other element. Moreover, Bohr's model did not fully account for the chemical behavior of atoms. In fact, although Bohr's idea of quantized energy levels laid the groundwork for atomic models to come, later experiments demonstrated that the Bohr model was fundamentally incorrect. The movements of electrons in atoms are not completely understood even now. However, substantial evidence indicates that electrons do not move around the nucleus in a circular orbit. Scientists in the mid-1920s, by then convinced that the Bohr atom was incorrect, formulated new and innovative explanations of how electrons are arranged in atoms. In 1924, a French graduate student by the name of Louis de Broglie proposed an idea that eventually accounted for the fixed energy levels of Bohr's model. De Broglie had been thinking that Bohr's quantized electron orbits had characteristics similar to those of waves. For example, only multiples of half wavelengths are possible on a plucked harp string, because the strings is fixed at both ends. Similarly, de Broglie saw that only odd number of wavelengths are allowed in circular orbits of fixed radius, as shown down below. He also reflected on the fact that light, at one time thought to be strictly a wave phenomenon, had both wave and particle characteristics. These thoughts led to de Broglie to pose a new question. If waves can have particle-like behavior, could the opposite also be true? That is, can particles of matter, including electrons, behave like waves? The de Broglie equation predicts that all moving particles have wave characteristics. It also explains why it is important to notice the wavelength of a fast-moving car. Why it is impossible to notice the wavelength of a fast-moving car. An automobile moving at 25 meters per second and having a mass of 910 kilograms have a wavelength of about 3 times 10 to the negative 38 meters. A wavelength far too small to be seen or detected. By comparison, an electron moving at the same speed has the easily measured wavelength of about 3 times 10 to the negative 5th meters. Subsequent experiments have proven that electrons and other moving particles do indeed have wave characteristics. De Broglie knew that if an electron has a wave-like motion and is restricted to circular orbits of a fixed radius, only certain wavelengths, frequencies, and energies are possible. Developing his idea, de Broglie derived the following equation, whereas a wavelength is equal to Planck's constant divided by the mass of the particle and the frequency of the particle. Step by step, scientists such as Rutherford, Bohr, and de Broglie have been unraveling the mysteries of the atom. However, a conclusion reached by the German theoretical physicist Werner Heisenberg proved to have a profound implication for atomic models. Heisenberg showed that it is impossible to take any measurement of an object without disturbing the object itself. Imagine trying to locate a hovering helium-filled balloon in a dark room. If you wave your hand about, you can locate the balloon's position when you touch it. However, when you touch the balloon, you transfer energy to it and change its position. You could also detect the balloon's position by turning on a flashlight. Using this method, photons of light reflected from the balloon would reach your eyes and reveal the balloon's location. Because the balloon is a macroscopic object, the effect of the rebounding photons on its position is very small and not observable. But imagine trying to determine an electron's location by bumping it with high-energy photon. Because such a photon has about the same energy of an electron, the interaction between the two particles changes both the wavelength of the photon and the position and velocity of the electron. In other words, the act of observing the electron produces a significant, unavoidable uncertainty in the position and the motion of the electron. Heisenberg's analysis of interactions such as those between photons and electrons led to his historic conclusion. The Heisenberg uncertainty principle states that it is fundamentally impossible to know precisely both the velocity and the position of a particle at the same time. Although scientists of the time found Heisenberg's principle difficult to accept and had been proven to describe the fundamental limitations of what can be observed. The interaction of a photon with a microscopic object, such as a helium-filled balloon, has so little effect on the balloon that the uncertainty in its position is too small to measure. But that is not the case with an electron moving at 6 times 10 to the 6, which is at about 6 million meters per second, near an atomic nucleus. the uncertainty of an electron's position is at least 1/1000th of a meter, about 10 times greater than that of the diameter of the entire atom. The Heisenberg uncertainty principle also means that it's impossible to assign fixed paths for electrons like the circular orbit in Bohr's model. The only quantity that can be known is the probability of an electron to occupy a certain region around the nucleus. So if we kind of look at 514, when we go ahead and have an electron in a given position, right, we can go ahead and know its position, but when we do go ahead and observe it using some sort of a photon, right, light, that photon has enough energy to go ahead and bounce around that electron. All right, and when it bounces around that electron, we kind of disrupt where this electron is going to be. And this is kind of the illustration of the Heisenberg uncertainty principle. Right? It's impossible to know at the same time the position, as well as it's almost impossible to know the velocity of a given particle. In 1926, Austrian physicist Erwin Schrödinger noticed that the wave-particle theory proposed by de Broglie. Schrödinger derived an equation that treated the hydrogen atom's electron as a wave. Schrödinger's new model for the hydrogen atom seemed to apply equally well to atoms of other elements, an area in which Bohr's model failed. The atomic model in which electrons are treated as waves is called the wave mechanical model of the atom, or the quantum mechanical model of the atom. Like Bohr's model, the quantum mechanical model limits an electron's energy to certain values. However, unlike Bohr's model, the quantum mechanical model makes no attempt to describe the electron's path around the nucleus. The Schrödinger wave equation is too complex to be considered here. However, each solution to the equation is known as a wave function, which is related to the probability of finding the electron within a particular volume of space around the nucleus. Recall from your study of mathematics that an event with a high probability is more likely to occur than one with a low probability. The wave function predicts a three-dimensional region around the nucleus called an atomic orbital, which describes the electron's probable location. An atomic orbital is like a fuzzy cloud in which the density at a given point is proportional to the probability of finding the electron at that point. Down below, this illustrates the probability map that describes the electron in the atom's lowest energy state. The probability map can be thought of as a time exposure photograph of the electron moving around the nucleus, in which each dot represents the electron's location at an instant in time. The high density of dots near the nucleus indicates that the electron's most probable location. However, because the cloud has no definite boundary, it is also probable that the electron might be found at considerable distance from the nucleus. So here's 515. The density map represents the probability of finding an electron at a given position around the nucleus. The higher the density points near the nucleus shows the electron is more likely to be found close to the nucleus. So as you see, right, in looking at A, that little dot, those little dots represent probabilities of finding the electron. Because we have a larger cluster near the nucleus, that means that's probably where we're going to go ahead and find it. At any given time, there is a 90% probability of finding the electron within the circular region shown in illustration B. This surface is sometimes chosen to represent the boundary of an atom. In this illustration, the circle corresponds to a projection of a three-dimensional sphere that contains the electrons. Right? And that's kind of how we kind of think about it, right? Think of some sort of spherical boundary, quote unquote, in which these electrons are in. Because the boundary of an atomic orbital is fuzzy, the orbital does not have an exact defined shape. To overcome the inherent uncertainty about the electron's location, chemists arbitrarily draw an orbital surface to contain 90% of the electron's total probability distribution. This means that the probability of finding the electron within the boundary is about 9/10, and the probability of finding it outside is about 1/10. In other words, it is more likely to find the electron close to the nucleus and within the volume defined by the boundary than it is to find it outside. And we'll go ahead and we kind of explained that in figure 515b. Right, in that circle, that sphere, right, is about where we would have a 90% probability of finding that electron. Recall that Bohr atomic model assigns quantum numbers to electron orbits. Similarly, the quantum mechanical model assigns 4 quantum numbers to atomic orbitals. The first one is the principal quantum number, n, and indicates the relative size and energy of atomic orbitals. As n increases, the orbital becomes larger. The electron spends more time farther from the nucleus, and the atom's energy increases. Therefore, n specifies the atom's major energy levels. Each major energy level is called a principal energy level. An atom's lowest principal energy level is assigned a principal quantum number of 1. When the hydrogen atom's single electron occupies an orbital with n equals 1, the atom is in its ground state. Up to 7 energy levels have been detected for the hydrogen atom, giving n values ranging from 1 to 7. Principal energy levels contain energy sublevels. Principal energy level 1 consists of a single sublevel. Principal energy level 2 consists of 2 sublevels. Principal energy level 3 consists of 3 sublevels, and so on. To better understand the relationship between the energies levels and sublevels, picture the seats of a wedge-shaped section of a theater. Right? Kind of look at it like this. As you move away from the stage, the rows become higher and contain more seats. Similarly, the number of energy levels in a principal energy level increases as n increases. Right? So as you go up energy levels, you're also increasing in energy sublevels. Sublevels are labeled S, P, D, or F according to the shape of the atom's orbitals. All s orbitals are spherical, and all p orbitals are dumbbell-shaped. However, not all d or f orbitals have the same shape. Each orbital can contain, at most, 2 electrons. The single sublevel in principal energy level 1 corresponds to a spherical orbital called the 1s orbital. The 2 sublevels in the principal energy level 2 are designated 2s and 2p. The 2s sublevels correspond to the 2s orbital, which is spherical like the 1s orbital, but just larger in size. The 2p sublevel corresponds to 3 dumbbell-shaped p orbitals designated 2px, 2py, and 2pz. The subscripts x, y, and z merely designate the orientation of the p orbitals along the x, y, and z coordinate axes as shown below. Let's just kind of give you a visual of what we're talking about, right? Your 1s orbital takes on a spherical shape. Your 2s orbital also takes on a spherical shape, but it just gets larger. Right? And again, that would increase as well as you have 3s, 4s, 5s, 6s, 7s, right, etc. Right? They'll just get larger in size, but still stay spherical in shape. And the same thing goes for your p orbitals, right? Your p orbitals take on this dumbbell shape, right? Whether it's px, which falls on the x-axis, your py falls on the y-axis, and pz falls on the z-axis. Right? And again, as you increase the principal quantum number, you're also going to increase the size of these dumbbell shapes as well. Where we at? All right. Principal energy level 3 consists of 3s, 3p, and 3d. Each d sublevel relates to 5 orbitals of equal energy. 4 of the d orbitals have identical shapes, but different orientations along the x, y, and z coordinate axes. However, the 5th orbital, dz squared, is shaped and oriented differently than the other 4. These shapes and orientations of the 5d orbitals I'll show you below. The 4th principal energy level, n equals 4, contains the f sublevel, which relates to 7 f orbitals of equal energy. The f orbitals have complex multi-lobed shapes, and I think they're excluded for a reason. If you want to find out what they look like, you can just Google it, and you can see how kind of bizarre they look. Okay? So to kind of just go on the d orbital, right? 4 of the 5 d orbitals have the same shape, but just lie in different planes, whereas the dz squared orbital has its own unique shape. Right? And here we have dxy, and this will fall on the xy plane. dxz falls on the xz plane. dyz falls on the yz. Then you have x squared minus y squared, which relate to these lobes falling on the x and the y axes. And again, a lot of these are derived through calculus, so I think it's a lot out of the scope of the course, but just kind of know the shapes of these. Right? Your s orbitals are spherical, your p orbitals are dumbbell, and your d orbitals just have this clover leaf shape, with the exception to dz squared. Hydrogen's first 4 primary energy levels, sublevels, and related atomic orbitals are summarized in table 5.2. Right? Whereas you have n equals 1, you only have s orbitals. N equals 2, you have s and p. N equals 3, spd. And once you get to n equals 4, you're going to have sp, d, and f orbitals. Note that the number of orbitals related to each sublevel is always an odd number, and that the maximum number of orbitals related to each principal energy level equals n squared. At any given time, the electron in a hydrogen atom can occupy just one orbital. You can think of the other orbitals as occupied spaces, spaces available should the atom's energy increase or decrease. For example, when a hydrogen atom is in ground state, the electron occupies the 1s orbital. However, when the atom gains a quantum of energy, the electron is excited to one of the unoccupied orbitals. Depending on the amount of energy available, the electron can move to the 2s orbital, to one of the 3 2p orbitals, or to any other orbital that is vacant. Section summary. Bohr's atomic model attributes hydrogen's emission spectrum to electrons dropping from higher energy to lower energy orbits. The de Broglie equation relates a particle's wavelength to its mass, its velocity, and Planck's constant. The quantum mechanical model assumes that electrons have wave properties, and electrons occupy three-dimensional regions of space called atomic orbitals.